Okay, so thank you very much for this very nice introduction. So as you said, today I want to tell you something about the research that we've been doing in the past few years in Strasbourg, and in particular at our new Center for European Center for Quantum Sciences, which is formerly a part of ESIS in Strasbourg. And so as you already mentioned, the story I want to tell you is today is about disorder in systems with cavity-coupled molecules. And I guess kind of the fundamental message I really want to get across is that disorder is really something cool because it gives rise to very interesting effects. It's not necessarily something that's bad for you in these type of systems. Okay, but before I really start, I want to just give credit to the people who did most of this work here. In particular, what I talk about today was really done by two PhD students. The one is David Wellnitz, who just finished his PhD earlier this year, and he's now a postdoc at Boulder at Schiller. And also another important PhD was Thomas Botzung, who is now a PhD in Aachen and Jülich. And important to mention also Stefan Schütz, who used to be a postdoc in Strasbourg, and he now went off to industry. And in addition, a lot of important permanent research collaborators on this are on the one hand, Jérôme Dubai, who is a CNS researcher in Nancy, which is a little town not far from Strasbourg, and David Hagenmüller, who is also here at the Institute, and Professor Guido Popillo. So as I said, there are exciting times at the moment because we just really, a few weeks ago, we moved to our new building. I have a picture of the building here at this new center. So it's kind of exciting times at the moment for us here. Okay, so just before I really start, I wanted to give you a more broader research background picture of what I've been doing in these past years so that you can more understand my approach to these cavity-coupled molecular systems. Because in general, my real research background is actually really physics, and it's really the numerical studies of quantum many-body non-equilibrium problems. So you consider, for example, any type of quantum many-body systems, preferably I like them to be on some type of grid. So these can be atoms, or think about electrons in a lattice or spins. And then there is some type of many-body descriptions in terms of this many-body wave function. And then what I'm interested in is studying the time evolution, really the real-time evolution, for example, according to a Schrödinger equation of the system on your classical computer. Now, of course, this problem has many different applications. And the real research background that I have is really coming more from ultra-cold atom physics, which is kind of a setup of very cool new experiments, especially in the last 10 years or so. These experiments, they develop very rapidly. And so nowadays, for example, one has really possibilities to engineer this type of many-body systems. So for example, one can use optical traps, controllable optical traps, to put atoms into nearly arbitrary potentials, and then one can have these atoms interacting with each other, and one can study really cool physics with this. And this is one application area of my research, and we are very closely working together with an experimentalist. This is Shannon Whitlock, who is also here in Strasbourg, and he's building a Rydberg atom experiment, which is supposed to become an upcoming quantum computation platform directly here at the Institute. So this is quite nice at the moment, but I don't want to talk about this topic today. Instead, I want to talk about our other big research topic, which of course also is an application of quantum many-body non-equilibrium dynamics. And this is really this research field of cavity-coupled molecules. And in particular, the inspiration for this type of work comes mainly from the experiments of Thomas Edison here at ESIS in Strasbourg. So probably in this webinar, I don't have to talk too much about this motivation, but clearly one of the starting works that really was an inspiration for us was this initial work in 2012, where they had the first observation that just by really using a collective cavity coupling of molecules, one can really modify chemical reactions. This was this paper here where there was this isomerization reaction, where one simply observed that if one is in the cavity and if one of those products is resonant, one electronic transition in those molecules is resonant with the cavity, then one observed that the reaction rate was actually slowing down. Now, what we want to do is we want to come from our physics perspective, and we want to try to understand this type of effect and what's going on really from a quantum many-body physics point of view. Another type of experiment that we are also very interested in is not chemistry, but it's really the question of transport. And this was really mostly inspired by this work also in the Abelson group in 2015, where they essentially observed that when they take an organic semiconductor and when one just puts an electronic transition in this organic semiconductor in resonance with, in this case, not with a cavity, but with a surface plasmon, but it's kind of the same situation. So if one has this scenario that one creates these hybridized polariton states, then in this experiment, they observed that they can drastically enhance the charge conductivity in the system, which is seen here by this boosting of these IV curves under strong coupling. And also for this is another example problem where we want to really come in and we want to try to put some physics perspective, quantum many-body physics perspective into this topic. So if I would describe it kind of in a sketchy picture, so what we are really trying to do is we want to do really a physics point of view approach. So what we do, what all physicists do, we try to describe the system with some kind of spherical cow model. So what we are doing is we are constructing minimal models which have all the necessary degrees of freedom, and we include this degrees of freedom really in their simplest form. So what do we need for these cavity coupled molecular systems? On the one hand, of course, we need electronic degrees of freedom. So in that case, the simplest possible system we can think about is just a two-level system, so two electronic levels. When we have, for example, like Pauli raising and lowering operators to go in between those electronic levels. On the other hand, obviously, we need the photon mode, we need the cavity, which is just a harmonic oscillator that couples equally to all of these electronic degrees of freedom. For example, with this well-known Tevis-Cummings type coupling. And then, of course, if we want to go to more chemistry type questions, we of course have to include also the nuclear degrees of freedom of the molecules. And they are the simplest way of doing this is by considering, for example, only harmonic vibrations of the molecules. And then these vibrations, for example, they couple again to the electronic degrees of freedom, for example, with some Holstein type coupling. And I will talk more about this later. So really what we are doing is just really this sort of bottom-up approach by consecutively making our systems more and more complicated and adding more and more degrees of freedom. And we want to really understand sort of by looking at the dynamics of this problem, we want to understand sort of fundamental effects which are behind this type of experimental observations. Okay, and what we did really so far is most of the work I think we did was really focused on what we would call an ultra cold regime. Ultra cold regime, I mean, initially that we had a situation that we say, okay, let's just forget about the nuclear degrees of freedom and let's just really take this Tevis-Cummings model and let's look at physics in this model. And with this, of course, one cannot do too much chemistry. We also applied this to some chemistry problem, for example, to some electron transfer reactions or also to some chemistry in the ultra cold, really. Some, for example, we had some work on the ultra cold molecule formation. But today, I want to, in this area, I want to mostly talk about the work that we did on transport. And that's going to be the first part of my talk. And then in the second part of my talk, I want to talk about this very recent work, which was actually just published yesterday. And in this work, what we did is now we added the nuclear degrees of freedom and we analyzed sort of the full electrophotonic nuclear dynamics, if you like. So the two parts of my talk, and they are really connected. And of course, in my title, I promised to talk about disorder. So I want to talk about disorder in these two types of scenarios. So in the first part of my talk, I want to introduce an effect that we discovered recently, which is an effect we called semi-localization. So I want to talk about disorder in cavity modified transport and the important role of these semi-localized dark states that we found in these two papers here. And then in the second part, I want to kind of tell you how this so-called semi-localized dark states that we discovered here can be important, because when you want to know how does vibrational dynamics in a cavity change, because these kind of semi-localized states, as you will see, they play a crucial role for cavity modified vibrational dynamics. So in the second part, I want to talk about this, and in particular, I want to talk about disorder enhanced vibrational entanglement. And if you don't understand what I'm talking about yet, don't worry, I will just go slowly and introduce these type of things. Okay, but first I want to start really with models where we have no vibrational degrees of freedom. So as I promised, I want to talk about transport, and I want to talk about transport initially really in the simplest possible scenario we can think about. And that's just a standard toy model where we have a bunch of two-level systems, and we have a single excitation in this chain of two-level systems. And we have a Hamiltonian in which sort of this excitation can hop from one side to the other one. This can be, for example, some first energy, resonant energy transfer, just for example. And of course, every time an excitation hops from one side to a neighboring side, I transport an energy of the level spacing from one side to the next one. Now, of course, if I would have only this type of excitation hopping, I couldn't study very interesting transfer properties. So in order to make things very kind of more interesting, what we have to do is we have to add some type of imperfections to the system. So imperfections, they can be really anything. They can be disorder, which I want to talk about today. But even when you have disorder, you can, for example, have some diagonal disorder in these level spacings, or you can have some off-diagonal disorders, for example, just some random offsets in these hopping constants. And then on the other hand, you can also have some open system noise. So for example, you have some spontaneous emissions of these two level systems, or you can have some dephasing processes. And the thing is just, if you have all of this type of imperfections and you throw all of these imperfections in your system, you see that normally what happens is that all these imperfections, they lead to an exponential suppression of excitation transport. And so what do I mean by that? So the way that we typically study these transport properties is what we do is we take our system that we have, and then we connect to one side of the system a very hot reservoir, which can put excitations into my chain. And on the other side of the system, we have a cold reservoir, which takes out excitation of my system. And then what we do is we write down a master equation for this problem, and we solve this master equation to go into a steady state. And then we can, for example, compute the steady state heat current that goes through the system. And this is what I show on the plot here on the right side. And you see here that as a function of the length of the system, here just for a one-dimensional chain, I see that this current just decays exponentially as a function of n. Note that this is a logarithmic scale here. And of course, this is a clear consequence of this type of imperfections, but we don't need all of these imperfections. Actually, this diagonal disorder is already enough to observe this exponential suppression of current. And the reason why this is the case is because of the very well-known phenomenon of Anderson localization, which is, of course, a very famously, very thoroughly studied problem. And I just want to introduce it here in the simplest form. So the simplest model that we can write now is, again, it's our system with the nearest neighbor hopping. So I have a Hamiltonian that really governs the hopping of excitations between sides. And here, I don't write it necessarily in a one-dimensional system, but it can be also like a higher dimensional system. And here, this notation with these little brackets just mean that the sum runs over all of pairs of nearest neighbor in your lattice. And then the only other term that one adds is this diagonal disorder, which is just a random energy offset on each of the lattice sides that I have. And typically one chooses this disorder in a certain window, which goes from -w/2 to w/2. So we have this parameter w, which just gives us a parameter for the strength of the disorder. And the reason why this is typically chosen as this uniform random distribution is so that one has a strict cutoff for this disorder range, so that one doesn't get any type of extreme outliers that make the math unnecessarily complicated. Okay, and then what happens in this system? This is a very simple system, but if one looks at the eigenstates of the system, then one simply sees that if this disorder is very weak, then of course my eigenstates are approximately just the normal Bloch states, which are completely extended over the system. But then at one point, if I make this disorder strong enough, I will see that my eigenstates actually have this localized form, which means that the eigenstates look like the ones I plot here on the right side. This is an example, simple numerical calculation, where on each of the sides in your system, the eigenstates are localized and they have these exponential tails on one of the sides. So they have this localization length parameter here. And then what makes this thing interesting is that if you go to a three-dimensional system, one can describe this problem really as a phase transition between extended states and between localized states. And of course, this has been studied for a very long time, and there's a lot of things known about this problem. What's important for us is really that this localization already leads to a suppression of the transport, which clearly has to go exponentially as the length of the system because of this exponential localization of these eigenstates. Now, what is very well known, and it's actually very easy to understand, is that if you add now a cavity coupling to the problem, you can really overcome this exponential suppression of localization. And this is very easy to understand. So here I wrote now the same Anderson problem Hamiltonian again, but I just add the standard homogeneous Tavis-Cummings model coupling to the problem, which essentially says that each of these emitters, they can emit a photon, and then any of the other emitters can reabsorb this photon, and this happens so fast that this is a coherent process. And then what one can see is, if one looks at this Hamiltonian term, what one can see is one can go into quasi-momentum space. I can, for example, introduce the discrete Fourier transform of these sigma operators here. And then what I see is that, of course, this Tavis-Cummings model, it only couples to the Q0 mode in this Fourier space. So it really only couples to the symmetric bright mode. And now what this means is that if I make now my collective cavity coupling strengths big enough, so in the sense that my G square root of n becomes much larger than both this hopping and both this order term. So if I forget just about the first part of my Hamiltonian, then I only have two eigenstates in my system, and they are the two polariton states, the upper and the lower polariton states. Now I show you these polariton states, for example, here in an example numerical simulation, where I have my localized eigenstates. But then I also have these polariton modes, which are now completely extended through the system, because these polariton states, they're a mixture of half the photon and half of this bright mode. And this bright mode is the Q equals 0 mode, so it has the equal weight in all of the chain. Now, it's quite obvious that these polariton modes can actually really drastically enhance the transport of the problem. And this is something which we studied already in 2005. We were not the only one to study this. But essentially what we found is that if you now study the transport, again, if you study this heat current as a function of the length of the system in the cavity, you see that in case where without the cavity one had this exponential suppression, now in the presence of the cavity one actually found the decay of this current, this goes as 1 over n squared. And using this polariton states, it's actually super simple to understand why this goes as 1 over n squared. It simply comes from the fact that this bright mode, of course, it has this normalization factor of 1 over square root of n, which means that in order to go into the bright mode from the left side of my chain, I have a probability that goes as 1 over n. And then I can, when I'm in this polariton state, of course, it's completely delocalized, but I have to go out of the state again on the other side of the chain. So I get another 1 over n, and in total, the decay goes as 1 over n squared. And so to say, just considering only these two polariton states in the system, it's already enough to understand this drastic enhancement of this energy transport that going from exponential suppression to 1 over n squared suppression. Now, however, the important question is now, what about all the other states in the system? Right? Because I don't only have two states, and it's a complete approximation to just neglect this first part of the Hamiltonian. And the other states in the system, which still exist, and they're called usually dark states, but it's a very confusing name because the dark states are actually not really dark if you have this order. So what I can do is I can take my Hamiltonian again, I can do this discrete Fourier transform now, not only of the cavity coupling term, but also of this hopping term. And a very simple calculation shows you that this hopping term also becomes diagonal in this quasi-momentum basis. So if I only would have this hopping term and I would only have this cavitative term, then of course I had my Q0 mode that couples to the cavity, and all the other modes, which are quasi-momentum modes, which are larger than 0, they would not couple to the cavity at all, and they would be really dark. However, I still have this disorder term, of course. And this disorder term, it's diagonal in real space, which means it's off diagonal in quasi-momentum space, which means this disorder term is going to mix my bright mode with all of the dark modes. And the fundamental question is now really what's the contribution of these dark states to cavity modified transport or cavity modified chemistry. And this has become, like here I selected a few papers, this has become a very interesting topic that people have studied now in the last few years. And for us, really one fundamental question we really wanted to answer is also really more fundamental question about what happens actually to Anderson localization and to this Anderson localization transition in this type of cavity coupled scenario. Okay, and to show you briefly that something interesting is really happening from these dark states, Here I show you one calculation, numerical simulations, looking at one particular quantity. And the quantity that I look here is what we call the return probability. It's a very simple quantity, so you can think about it in the following way. So we have our cavity and our system. And we ask now, let's say that you put an excitation on some site in your system, let's call it C. And then we ask, what's the probability to remain at that site if you let the system evolve as a function of time? And we want to make this quantity time independent. So what one does is one can compute the infinite time average of this probability. And then one arrives at this very simple formula for this return probability, infinitely time averaged. And it's a very intuitive formula. It just tells you it's C E alpha. E alpha is here an eigenstate of the system. And you have to sum over all of the eigenstates. And this formula essentially tells you the probability to stay at the site C is the probability to go from the state C into the eigenstate E alpha, which is C E alpha squared. And then you have to go out of this state again. So you get another square to get in total a power to the power of 4. Okay, and we look at this quantity now and ask what happens if we switch on this cavity coupling in the presence of disorder. And this is what I'm showing in this plot here. So in this plot, I show this return probability for a 3-dimensional system. So we take a cube, which is a 15 times 15 times 15 cube. And I show you this return probability as a function of this disorder strength W. Now, first look, for example, at the case without the cavity. There we just simply get exactly what we would expect. If we have a very disordered system, if we are over here, in the case that the disorder really overcomes all the other energy scales, we find that the return probability turns to 1. Why is this? Because in that case, we just have one localized state exactly at the site C. And this is the only state that contributes to this sum here. And this is just, this state is always going to be there, and this is going to give me a 1 in my return probability. On the other hand, if I make my disorder very small, then my states, they're going to be extended over the system. They're going to be Bloch waves. And then, of course, each of the eigenstates gives me a little contribution, but this contribution goes as 1 over n squared. And I have n terms that go as 1 over n squared. So here the return probability goes to 0 with the system size. Okay, this is all very simple. Now, the cool thing is now we have, look what happens when we turn on this cavity coupling here. This is the collective cavity coupling strength, turning it on slowly. And the interesting effect that I want to talk about today is that we see that we have suddenly this plateau in this return probability showing up here, where suddenly the return probability goes to a value which is sort of like roughly 1/2, in reality something like 0.4. And the interesting thing is that this value of 0.4 does not change with the system size. This is something that we checked numerically. And we find that this plateau really happens when you're in the strong coupling regime, like here, for example, where this collective coupling is overcoming both the disorder strength and this also the hopping amplitudes. Okay, so where does this plateau come from? And the effect, how we explain this plateau, comes from this effect that we call semi-localization. So let me introduce this effect. And to make things, again, even more simpler, let's just take, again, our Hamiltonian, but let's for a second just neglect this hopping term completely. And let's say that we only have this order and we only have this collective cavity coupling strength. So we're sending J to 0. In that situation, of course, if we have no cavity coupling, if we put the G to 0, the eigenstates are completely trivial because our Hamiltonian is already diagonal and our eigenstates are just perfectly localized states on all of the sides of the system or, of course, in the cavity. Now, however, if you now go to a strong coupling scenario, what happens is, I showed you before that the second part of the Hamiltonian has 2 eigenstates, which are the upper and the lower polaritons, which means now in terms of dark states, there are only n-1 dark states left, but I still have n sides in my system. So what happens is now that I have n-1 dark states and they want to localize because there's a strong disorder, but they have to localize on not one, but actually on 2 sides. So this is, I show you here in this little numerical calculation, 2 example eigenstates of the system. Here, a perfectly Anderson localized state with full only weight on one particular side. However, in the collective strong coupling regime, we see that actually the eigenstates look in such a way that they have now finite weights, not on one, but on 2 sides. And what you will find is that these 2 sides where these eigenstates have weight, they're actually sides which are close in energy here. They're not necessarily close in real space, but they're close in energy. And those type of dark eigenstates we call semi-localized eigenstates. Okay, I don't have very much time to introduce everything in detail, so I just want to, on the last 3 slides on this first part of the talk, I really want to give you kind of a summary of the effects that these semi-localized dark states exhibit. So here on the top of the slide, I have a kind of a summary of the effect. On the left-hand side, I show what would happen if you have no cavity and you have strong disorder, which is a scenario when you would have normal Anderson localization. And in that case, you would have all your random eigenstates just distributed in this window of plus omega 2 and minus omega 2. And they're just randomly distributed in there. And you have the cavity, which in our model, we always chose to be on-resonant in the middle of this spectrum. What happens in the semi-localized phase is that you have these 2 polariton states which emerge outside of this window of this disordered energy range. And the other n-1 localized dark states are now new eigenstates which are energetically in between those old eigenstates. And those are the ones that have weights on different sides in your system. Okay, this again just for a summary of the effect. Now, what's the cool properties of the effect? The first really, if you talk about localization, people usually talk about the so-called inverse participation ratio, or the IPR, which is essentially a measure for how localized the eigenstate is. So it's defined for a particular eigenstate of a particular energy. I'd give the definition over here. And you see it has a very similar form as the return probability. It says also this to the power of 4. And it's essentially the way that you can think about the IPR is kind of like the contribution of a single eigenstate to the return probability. And it's just a number that it goes to 1 if the state is localized, and it scales to 0 if the system size if the state is delocalized. Now, in the normal Anderson localization picture, you find that this IPR is typically a number which is, if you increase the disorder, it goes towards 1, and it's constant. It does not scale with the system. On the other hand, in the semi-localized states, these eigenstates, they have this value of 0.4, and they're also constant. So they are kind of localized, similar, but they have IPRs which are at a constant value, but at a smaller value than 1 if you increase the disorder. That's one cool feature. Another important measure for localization, if you go to this localization community, it's always the level statistics of your localized states. So what does that mean? It means essentially that you just look at your states here in this disorder window, and then you define an energy difference between 2 eigenstates, and eigenstates alpha plus 1 and alpha, and you find the energy difference, and then you compute the distribution function of these energy differences. Now, of course, when you have a completely localized system, you will find that the state energies are just randomly distributed, which means that your distribution is going to be a Poissonian distribution. And then for the normal Anderson localization, one finds that this distribution changes when you cross this transition to delocalized states, in the sense that this Poissonian distribution goes to a so-called Wigner-Dyson distribution. Now, we check the same property for our semi-localized states.
I'm sorry, Professor. Before you continue with what happens in the other case, okay. I think there is a couple of questions. Okay, one is Kajit Mandal, and then Professor Keshavamurthy. First, Kajit Mandal, please.
Yes. Hi. Could you hear me? Yeah.
Yes.
Hi, Professor. Thanks a lot for the interesting talk. My question is that in the Hamiltonian, you are considering one cavity mode, which is essentially k equal to 0, right? And so it couples to the bright mode, as you showed when you go to the Fourier space. Now, the dark states that you have, which I think they will couple to other cavity modes, which have non-k, like k not equal to 0, right? And in those cases, the dark modes are not really dark in that they're still coupling to some cavity modes. So how would your conclusions change, do you think?
So, but yeah, this is exactly, so you're saying even without disorder, there's a coupling? Or with disorder?
Even without disorder, right? Because so I mean, like, you have the polarization direction of the main cavity mode,
yeah.
And then you have the other direction that is non-quantized, right? And that would have k values that would couple to these dark states, right?
Okay, so I have a bunch of approximations that I was kind of ignoring here. So what I talk about is a scenario where I essentially have a system which I still consider translational invariant, or I consider it infinite. I think maybe that's what you're talking about, because of course in reality in reality I have like not an infinite system. I have like a finite system. If I take a one-dimensional system, I should actually, when I do my Fourier transform, I should not use the discrete Fourier transform into plane waves, but I should use a discrete Fourier transform into particle in a box wave functions. And then those would be my bright modes and my dark modes. What this would of course mean is then if you have the hopping term in the Hamiltonian, the first term here, then of course this hopping term, it would not be exactly diagonalized anymore, and I would get also some mixing. But I don't consider this. As I said, I mean, this is really a spherical Cow model. So I consider a toy scenario where really all of the molecules, they couple precisely with the same strengths to the same cavity mode. And I have a scenario where my system is so large that I consider it to be infinite. And if it's infinite, then it's also translational invariant. And then my discrete Fourier transform really diagonalizes this first part and it diagonalizes the second part. And then I have no term in my Hamiltonian in which the BQ zero mode couples to these BQ larger zero mode terms. Of course, in a real system, which is finite and which has some inhomogeneity also in the cavity coupling, I would also get this mixing. But here I really want to just see what happens from diagonal disorder, from the mixing that comes from the diagonal disorder to the dark states. Did this answer your question, or were you referring to something else?
Yeah, sure. Fair enough. I mean, that's fine. Thank you.
So at least in this toy model, if you really turn off the disorder here, then there's no mixing between the bright mode and the dark states.
Okay, now Professor Keshavamurthy, you can unmute yourself.
Yeah, my question was on this interesting thing that you had this IPR in the presence of this semi-localized states, that is always around 0.4. So the way I understand it, that the IPR essentially means that these eigenstates and only the two states which are contributing to these eigenstates. Why is it independent of n? That's a little bit puzzling.
Yes, I mean, this is the reason why it's 0.4. It really becomes from eigenstates like this, right? And what you do is you compute the return probability for starting at a particular site, and let's say you choose this site here, right? And then you see this site here. Of course, it gets a contribution only from this weight of the eigenstate, but not of this one. So the other one is lost. So in the end is what one sees is the same that happens for like relocalization, right? In relocalization, if you make the disorder stronger, these states, they get stronger and stronger localized. And in the end, I just have ideally eigenfunctions which are approximately just delta functions on each of the sides. And then my IPR is going to be 1 because I have one eigenstate that contributes here, right?
Right. I guess the related question was that, if you said something that is important about the two states on which there is this localization, that they are nearly degenerate, right? These dark states.
Yes, exactly. They are close in. Yeah.
Right. I'm sorry. So generally, to me, that suggests that there is some sort of a frequency matching between these guys, some sort of a resonance, which if you cite this hopping term, then it would be like, it would probably get enhanced in some sense.
Right, but only, as I will show it does not. Okay, right. I will show you this exactly with when you talk about the level statistics I was just talking about. But here it's really it's not really a resonance condition. It's really that this new eigenstate that you have, right? They lie in between energetically of the two old ones here. Right, so in a way, what they become superpositions of this state and of this state. So you have two localized states that hybridize with each other. And those states are the new ones which are energetically in between. And this, of course, is drawn in the energy space. but in real space, these amplitudes there can be like arbitrarily far from each other. But because those states, they're kind of hybridized states from these two other localized states, they still have kind of this property that the IPR is not going down.
I see.
And in terms of what happens if you now turn on the hopping also. So what really also happens, and let me just make this one point here, is that I just wanted to say is for local localization, when you have fully localization, you have the Bosonian statistics. And then if you turn on the J, you get some type of level repulsion between those states. And that's the origin of why you go from this Bosonian statistics to this Wigner-Dyson statistics. And what we see is like for the semi-localized state, we find the same type of level repulsion. So this is seen here in this plot of this level spacing statistics that at short distances, like the states are suppressed, so they still repel each other. But we still don't find the same distribution function as for delocalized states because we find a different tail compared to the fully delocalized state. So we find this semi-Bosonian PDF in this case. So in the end, it's not like that if you add some hopping, this helps, but the hopping actually leads again, like because from here it also leads to some level repulsion. And I would guess if you think about it, that you add the hopping, it actually really also adds some additional level repulsion. So it's actually fighting this localization.
Oh, I see. Yeah, indeed. Yes. That's, I understand that. Yes. Yeah. Thank you very much.
Okay.
There is 2 more questions, but how we can go quicker with this? So Sindana and then Professor Paul.
I have a question, which is a follow-up on the first question by Arkachit just before now. So I think you're considering a single cavity, right? But instead, if you have a multi-mode cavity and then even without disorder, each of the different things that you consider as dark states here would couple to the different cavity modes, right? How would that affect your transport calculations?
I don't know. simple answer. Really, what we're trying to do is we try to single out different effects and how they contribute. And what I'm really showing you here is I want to single out the effect of how the diagonal disorder, the mixing that comes from diagonal disorder, changes your states. It's an interesting question. I really cannot answer it. It depends how big the mixing effect is from the fact that you have a multimode cavity. But if this effect is, for example, small, and if your disorder is large enough, I would guess that the mixing that comes really from the disorder that I'm showing here is the dominating term compared to the mixing that comes from the fact that you have a multimode cavity. But again, we haven't looked at this. It's an interesting question actually to look at.
Okay, thank you.
Professor Hoyle.
Hi, Johannes. Thank you for this very nice talk. So I have a comment and a question very quickly with respect to Arkajit and Sindana's question. So I think for a multimode cavity, I mean, it's not that if you have n molecules, you also have n modes, right? Like the number of molecules always exceeds the number of cavity modes, and therefore I still expect this phenomenon that you are talking about to hold, like these semi-localized states. But the question I really had was, you said that you talked about the scaling of the transport as 1 over n times 1 over n squared due to the polarity on states. But then can you comment how this semi-localization changes the scaling that you discussed?
That was my next slide, exactly.
Oh, okay, sorry.
Because this is, okay, I'm sorry, I don't have the time to really show like calculations here in detail, but the really cool thing is now that really when you look at the transport properties from these semi-localized states, we find that they also give a 1 over n squared contribution with one big problem that I kind of like ignore here, because they show a 1 over n squared contribution, of course, if you consider the disorder averaged scenario. Right, so what essentially happens is, I mean, sort of just imagine you have a 1D situation, and just imagine you have a really super lucky disorder configuration where you have the first site is just almost at the same random energy than the last site in the system. right? So then you will have one semi-localized state which has a weight on the first side and a weight on the last side. And then for this state, I can, no matter how large my system is, I can almost perfectly get energy through this independent of n. But of course, this is only one state of many states in the system that can appear. So if you do the whole calculation, if you take a disorder average over the system, what you will find is that in a disorder average picture, these dark states, they also give you a 1 over n squared contribution. But that contribution is going to be very noisy and very disorder dependent. And that's one of the main outcomes.
I don't understand that statement. So if you have this lucky configuration that you have semi-localized states next to the reservoirs, sure, you have perfect transport into those semi-localized states, but then you still need to go through the entire bulk. So then through the entire bulk, don't you get again these 1 over n squared factors?
No, but no, you don't, because you have one eigenstate. It's a coherent problem. You have one eigenstate, and this one eigenstate has like weight on the first side and weight on the last side, and it has a large weight on the first and the last side.
I see. I get it.
But it's not like the polarity mode has a weight that is distributed over all the system, and it goes smoothly down if you make n larger. But this state has really a weight that does not scale with n on the first side and on the last side. So this state happens, but of course you have to be super lucky to get this realization. So what you have to do is you have to do all the calculation with all the statistics, and then you find that if you average over everything, then the semi-localized states give you a 1 over n squared contribution.
Okay, so just one last question, just to clarify, when you had the 1 over n squared scaling in your numerical calculations, you already considered the dark states, or yes. In that? Okay, you did. Okay, thank you.
That was a full numerical calculation. You only had an analytical result that says analytically it should go as 1 over n squared from the polariton states. But the numerics included already the dark states in this calculation.
Thank you.
Okay, and the last thing from this first part of the talk I want to really highlight is that we have the most recent paper that we published on this is it's actually very cool, because all of the results I show you here, they're not just numerical results, they're actually also fully analytical results if you go to the limit where this hopping is 0. Because if you turn this hopping 0, then the form of your Hamiltonian has this so-called arrowhead shape, because it looks like the head of an arrow, and it's a random arrowhead Hamiltonian. And there's this whole theory about random arrowhead matrices that allows you to really get analytical solutions for all of these properties that I was talking about here. And it's really this hopping here is really not important in the regime where we are in any way, because we're interested in a localized regime where the disorder is already much larger than the hopping, and then there's the cavity coupling, which is still much larger than this. So that's quite cool. That was this latest work here. Okay, but now I guess this is a good time to go to switch to the second part of my talk. And I want to show you now one of these consequences of these semi-localized states, now also on the vibrational dynamics of molecules in a cavity, referring to this latest work that we just published. So the way that I want to take the next step to include vibrations, it's a spherical cow approach, in the sense that we want to look at the simplest possible model for nuclear degrees of freedom. And that's simply, imagine you have a molecule and it only has one nuclear coordinate. So imagine like you have a diatomic molecule and you have some distance. And then we say we have two potential energy surfaces. So depending on whether we are in the electronic ground state or in the electronic excited state. Now, what we just consider here for now is, let's say we are always close to the minimum of those two potential energy surfaces, and we make a harmonic approximation in this minimum in such a way that we have harmonic vibrations in this minimum, and that's all we consider. And then, of course, what I get is typically the minimum is different in the excited state and in the ground state, simply because a different electronic configuration gives rise to a different equilibrium position of these nuclei. And then this gives rise to this well-known Holstein coupling term, which essentially really only means that if I am in the excited state, so if I have an electronic excitation, then the position of my oscillator has to shift. And it has to shift by a certain amount lambda here, square root of 2 lambda, and that's this that couples the electronic with the vibrational degrees of freedom. And now if I add also the cavity to this, I arrive at this Holstein-Cummings model. And of course, if I have, for example, only this Holstein term, I could easily analytically do a diagonalization of this term. just by doing a displacement transformation of my operator, B here. But of course, we want to again study the full system where we also have disorder where this is not possible. So the full model that I want to talk about now is a disordered Holstein-Terwitz-Cummings model. So we have a diagonal energy disorder term, the same that I introduced before, that gives rise to the semi-localization. Then I have my Terwitz-Cummings coupling, I have my Holstein coupling, and I have, of course, the vibrational oscillator energies. And what we wanted to know now, inspired by these very old experiments in the Everson group, we wanted to know what happens if you do kind of photochemistry with this. So if you do an incoherent excitation at sort of the optical frequency in the system. And importantly, what also it's a bit of an outcome of this work, it's really important to distinguish the scenarios where you either incoherently excite a single molecule in your ensemble, or where you incoherently excite actually the cavity mode. This can give rise to very different physics. And what we wanted to do now, we wanted to ask, okay, what happens if I have this excitation? How does my quantum state, which is initially in the equilibrium ground state, how does this quantum state evolve on a very short femtosecond timescale? And this is a very challenging problem because, of course, this whole problem has a huge Hilbert space. So, and it's very difficult to solve this numerically. And now here, maybe as a little surprise twist, the quantity that we were particularly interested in was the evolution of quantum entanglement in this system. And so that this, in order that this does not just come out of the blue, I want to take here a little detour about this entanglement entropy and why we're actually interested in this quantity and what it means for our system. So this is just a few slides giving you just a basic introduction about what I mean when I talk about entanglement entropies. So what I mean is simply consider you have a many-body quantum state. It can be anything, can be spins, or it can be electrons, or whatever you like. It's a many-body state, so it has many small constituents. And let's say I define a Hilbert space on one block of my quantum state, say block A, and a Hilbert space on my block B. Then this state, I can define some entanglement between this block A and this block B, simply by saying that it is a state that I cannot write as a product state. So any state of my total system, if the state is a pure state, any state which I cannot write as a product state, which I cannot write in this form here, is entangled. That's the definition of entanglement. Now, the important question is like, how much entanglement does it have? And the way that one defines this entanglement measure for this system is that one looks essentially at the reduced density matrix of my subsystem A. So what I do is I take my subsystem A, I ask what's the state in the system A, quantum mechanics 101, I have to trace over the system B, and then I get a density matrix. And then it depends now on the purity of this density matrix. If this density matrix A is a pure density matrix, then the total state has to be a product state. However, if it's mixed, then the total state has to be entangled. So what one does is one now defines the entropy of this density matrix. One can choose the von Neumann entropy or other entropies, doesn't really matter. And then the entropy of this reduced density matrix gives you a number, and this number tells you how much quantum entanglement is between the block A and the block B. And it's in general a quantity that's between 0, which means you have a product state, and the logarithm of the dimension of this Hilbert space A. So here, just as an explicit formula by, of course, trace rho log rho, I mean, I compute the eigenvalues of the density matrix P alpha, and then there are probability distribution, and I compute the entropy of this probability distribution. So to make this more intuitive, I have some very few super simple examples. Let's take, I have for an example where I only have 2 spins. I have a state where a spin is up and a spin is down. Then a trivial product state, for example, is just spin up, spin up. Of this state, if you compute the reduced density matrix, it will be just the projector on the spin up. And easy to see that the entropy of the density matrix is 0 because that's really that's a pure state density matrix. On the other hand, if I go to what's called a maximally entangled state or a Bell state, for example, I take spin up plus spin down, spin down. If I now compute the density matrix, I see it becomes an identity times 1/2. Right? So in that sense, I have a state which is a completely incoherent mixture with 50% up and 50% down, and this is maximum entropy, which is the logarithm of 2 because the logarithm of this dimension of this sub-Hilbert space. Okay, very simple. Now, in our problem, what we have been interested in is the entanglement entropy between the vibrational degrees of freedom and the rest of the system. And I will explain in a second why. So what we do is we really take our many-body state and we really take all of the electro-photonic degrees of freedom on one side. We call this our block A. And we have all the vibrational degrees of freedom in the other block, the block B. And we compute the entanglement entropy, which gives us a number that tells us how much quantum correlations are between electro-photonic degrees of freedom and between the vibrational degrees of freedom. Okay, so why are we interested in this quantity? Okay, I want to just very quickly go over this one slide. So one motivation is because these entanglement entropies, they are actually connected to the difficulty of computing quantum mechanics exactly on a classical computer. So they're connected to numerical complexity. And this connection, it's made by this so-called matrix product state. So what these matrix product states are, you can think about them as a generalization for product states. And while product states don't feature any entanglement, these matrix product states, they feature a finite amount of entanglement. So essentially what one does is one can write a quantum state, one can write a decomposition as a quantum state as a matrix product where the entries of matrices are themselves little local quantum states. And then one has this additional parameter, which I call here the matrix dimension. And then one can show that if I decompose a state like this, then I essentially limit this entanglement entropies to a maximum number of the logarithm of this matrix dimension. What this means is, now the important thing is when I have now some quantum dynamics that produces large entanglement entropies, then it means that this type of efficient numerical technique is starting to break down because my matrix dimension has to become very, very large. So in a way, this tells you directly the question how much entanglement entropy I have in my system is directly connected to the question of how efficiently I can simulate quantum dynamics on a classical computer. And it's a very well-studied field. I don't want to go into the details, but that's one motivation why we really look into these type of entanglement entropies. Now, if you're not familiar with this, I give you a very simple example of why this is connected to sort of complexity. And this is connected to now this entanglement entropy that we were looking at. I told you we write our state in such a way that we shift all of the vibrational degrees of freedom on one side, and now we compute the entanglement entropy. Now, for example, imagine that this entanglement entropy between these two blocks would be 0. That means that I could write my state of the system as a product state between electrophotonic degrees of freedom and vibrational degrees of freedom. So this would be kind of the Born-Oppenheimer approximation, if you like. And if we have this entanglement being large, then Born-Oppenheimer will clearly break down and one has to go beyond this. That's an intuitive explanation of how this entanglement is just connected to complexity. So the cool thing, what we did is we used sort of this matrix product state idea to write a code that could now allows us to simulate full exact electrovibrational photonic dynamics of large number of these toy model molecules. We could go up to something like more than 150 molecules actually. But I don't have time to really go into the details of this code, but believe me, it's very cool. Okay, but now let me go show you the results that we get. First, really looking at these entanglement entropies. So I take our model, we take a disorder model. Now for this work, we took actually a Gaussian disorder of a width W, which is a bit more realistic in terms of realistic systems. And for the first surprising result that we kind of found is the plot here on the right side. So what I show you, we choose parameters which are kind of semi-realistic for some type of experiments. And I show you here the evolution if we put an incoherent excitations in one of the molecules. And I show the evolution of this vibrational entanglement over a time scale which corresponds to one vibrational period of this oscillator here. And then the surprising thing is, if you see as a function of the disorder strength, if I increase the disorder, actually this entanglement increases, which is something we didn't really expect because usually you expect disorder destroys entanglement and it makes things more simple. But here actually, the disorderless case gives you an evolution which has barely any vibrational entanglement. But then if you make the disorders larger, this entanglement starts to grow. So why is this the case? And that's what I want to explain now on the last slides of my talk. And so spoiler, this is I will show you that this is connected to the semi-localized states. But to understand this better, let's have a closer look at really the dynamics of the system that we find. So I take the same exact parameters that I showed you in the previous plot. I take a fixed disorder strength of here GC over 2, and I look a little bit closer at what happens now for a single disorder realization for the phase-space dynamics of all of these oscillators of the molecules. So this here is a phase-space plot. It's plotted the position of the oscillators versus the momentum of the oscillator. And you see one line here that is shooting up. And this is the line for the phase-space plot for the oscillator of the molecule that's initially excited. And this is making this huge, huge phase-space circle. Note that here, this is a very small scale, it's 10 to the minus 3. Okay, and the next line I want to explain is the one you barely see it, but there's a tiny gray circle that's very small here. And that's the result that you would get for all of the evolution of the oscillators of all of the other molecules if you wouldn't have any disorder in the system. So it's really barely visible. It's a very tiny, tiny effect. However, what happens now if you have disorder, and these are all these red lines here, these are all oscillators for different molecules, you see that now with disorder compared to the disorder-free case, you see a much more pronounced dynamics of the vibrational dynamics of these other molecules. And the reason why this is coming from is because the disorder is going to transfer the excitation in the system in a different way than in the disorderless case. And that's what I want to, this message I want to transfer with the plot here on the right-hand side. So what I plot here, it's the electronic occupation of all these oscillators when I now order it in terms of the energies in my disorder configuration. And again, I see if I don't have any disorder in my system, I see that I distribute the initial excitations to all of the other molecules, but just a tiny little bit. The reason why I only transfer a tiny bit is because, of course, I have to first put excitation into the polariton mode. And then from this polariton mode, I have to put it onto some other molecule. And it's a very small effect that goes down as 1 over n squared. So this is going to be very small. So all of the other oscillators barely don't see any excitation. That's why they don't undergo any dynamics. However, now what I see in these red dots here, I have here this vertical line. The vertical line is the energy of my initially excited molecule. And I see that all of the molecules in the more or less in the energetic vicinity get a much larger excitation fraction, electronic excitation fraction. And because they're now having a larger electronic excitation fraction because of this Holstein term, they start to have some vibrational dynamics. Okay, maybe from these plots, it's a bit tough to understand. So I just made a little sketch again to really explain how this effect really works. So the way that it really works, you have this single excitation, it's going into one of the molecules. And then because we have a disorder enhanced energy transfer, which is exactly a consequence of the semi-localized states that I introduced earlier, this excitation will be very efficiently transferred to other molecules in this ensemble. It's not necessarily molecules which are close to it, but they can be arbitrarily far, but they are the ones that correspond to the semi-localized states which have a weight on this molecule. And then because they have these excitations, they start this different out-of-phase molecular dynamics, and they all get a different weight, so they all have a different out-of-phase dynamics. And because of this all complicated dynamics, we get this large vibrational entanglement in the system. And that's our explanation of this effect. Okay, now to not make it just a very abstract effect, I want to also say that this entanglement, this order enhanced entanglement that we find, it can also have some actually real physical implications of the system. So in order to see this, what I show you in this plot here is now I go to a time or one oscillation period, and I now look not only at the position of these oscillators in my phase-space plot, but I look at the full distribution of the nuclear coordinate. So these lines that I show you here, they are really probabilities for being displaced from the equilibrium position in the oscillator after one oscillation period, after I had my whole many-body excitation dynamics. And there are two interesting effects that you now see when you start to increase the disorder. So on the one hand, there are two lines. There's a gray dashed line. This is just this result completely without the cavity. There I just put an excitation onto one molecule, and because the excited state is shifted, it just undergoes this phase-space dynamics. So, and then you get this distribution, which is this Gaussian gray dashed line here. Now, if you do have the cavity, but you don't have any disorder in the system, there's barely any change. I mean, there is a change if you would zoom in, but you really don't even see it on this scale. And this is just because there's barely any excitation transfer away from the molecule without disorder. However, what now happens if you increase the disorder, you see that distribution, it starts to shift to smaller values, right? And we understand this, but we understand this even without entanglement, because we can understand this from kind of like a mean field shift picture. Because if I would, for example, factorize my vibrational degrees of freedom from the rest, my Holstein term would look something like this. It would depend on the excitation fraction on my individual molecule. And since this is the distribution for the molecule that I initially excite, the disorder leads to excitation transfer away from this molecule, which means that the effective position of this oscillator starts to shift to smaller values. And that's exactly what we see. We see that this nuclear distribution starts to shift to smaller values. However, there's also another effect then, which is actually really cool, because we could show that this effect is really connected to this entanglement. And that is that you see that also this distribution really gets this kind of non-Gaussian shape, right? Because you see it gets a bit tilted in the sense that, for example, here you see the weight on the left side is getting a bit higher and the weight on the right side is getting a bit lower. So what we wanted to do is we wanted to look a bit more at this kind of weird shape of the distribution. So the way that we did this, we looked at the extreme configurations. So what we do is, and I will define it on the next slide more clearly, we define sort of a weight of the distribution, which we call a tail weight, which is a probability for being sort of in a very far region away from the center of this Gaussian distribution. What we had in mind, or why we defined this quantity in such a way, is because we kind of thought naively, maybe if you go to chemistry later, then this extreme configuration could, for example, be connected to some bond breaking and could have some consequence on some chemistry, but I'm not claiming to explain any chemistry here really. Okay, but we wanted to know now what happens to these extreme configurations. And so here,
yeah. Sorry, Professor, before you continue with this slide, there's a question from Margaret. Margaret, you can go ahead.
Hello, can you hear me?
Yes.
Okay, so I have a question about the last slide. Yeah, so here you were saying, here you have that picture that if you excite one molecule, it sort of goes to many different molecules, but like the excitation goes to many different molecules, and that leads to this phase-space dynamics where all the molecules move, right? But then if the semi-localized state are localized across just two molecules, shouldn't just like two of them move? Like, why does, if you excite one, it gets transferred to all and not just the two on which the state is delocalized?
Yeah, because the localization on two sides is a simplified picture. The reality is actually a bit more complicated. In the semi-localized case, you already noted that this return probability was not 1/2, but it was actually 0.4. And that's actually because the semi-localized is not really always two sides. It also has weights on like a third side and a fourth side. And that's what you see when you do the exact analytical calculation. So that was the picture with this localization peaks on exactly only two sides. That was really an oversimplified configuration. In reality, you find much more complicated configurations.
So normally they are localized over all different molecules. Is it like that?
No, but you have like sometimes you have configurations where you have a weight on one side, another side, and then you have it also a very large part on the third side. That's because you have a random configuration where you have three states which are very close in energy. And then also all of these three, they hybridize together. And then you have weights on not only two, but on more sides.
Okay, and I have one more follow-up question. So you say coherent out of phase vibration. So how do you define coherence here when you're doing classical dynamics? I mean, what do you mean by this coherent out of phase motion?
I just mean, so what I mean is you look at these oscillators here, they all evolve differently. Right, so if you go to this W0 case, let me go to the previous slide. If you go to this case where you don't have any disorder, you have sort of all of the other molecules, they take the same type of dynamics. So again, in this regime, you can approximately describe it just by one bright symmetric vibrational mode that just oscillates. Right, so in that sense, you only have one vibrational mode, and then this is the reason why you don't have much entanglement here with the rest, because there's only one mode that gets entangled with the rest. However, here I have now vibrations that all go differently, they all go out of phase. So I have many modes that entangle with the rest, and that's why we have a large entanglement.
Isn't that just because like you have different frequencies? I mean, because now the frequency sort of is distributed because of this disorder. Is that's the cause of this different dynamics, right?
Yes, yes, exactly.
Okay,
But also the fact that they get a large amount of excitation because there's only smaller excitation in the disorderless case. So it's a combined effect. These do get a large excitation, so they start to have some vibrational dynamics. And also because of the disorder, each of them evolves differently.
Okay, I see. Thank you.
Also, one other thing I should say, of course, you also have this vibrational coupling term. This is also a term that already mixes the darks and the bright states, right? So you also get some mixing from this, which even more makes this semi-localized state picture, of course, too naive. I mean, the reality is much more complicated, but it's just a simplified mental picture to help us understand what's going on.
Okay, I see. Thank you very much.
And now Professor Wei Xiang.
Hi, yeah, great talk. I have some quick questions. So how long would this entanglement last? Like, I assume that it's going to dephase quickly.
Yes. I mean, all I'm showing here is one vibrational period only. So we're really talking about femtoseconds in typical metal setups here. And also, I mean, just a warning here, the quantity that I plot as entanglement, it's again a disorder average entanglement. So it does not really mean entanglement. It's like for each disorder realization, you would get this entanglement quickly, but then also because you have disorder, if you look at this in a disorder average picture, also this kind of would mean that this quantity, disorder average, is not real entanglement anymore. So I'm not claiming that you can do sort of EPR experiments in these molecules, but I just use this quantity as a quantity that tells us how much numerical complexity is there between vibrations and electrophotonic degrees of freedom.
Right. Yeah, got it. Thank you. The other question is, I'm a little bit confused about the origin of this entanglement, as I think the eigenstate here for both the dark mode and the polariton mode themselves is not entangled, right? So is it because of when this initial incoherent excitation, populated, goes to different type of dark mode and there is a superposition between them, or what do I think about it?
Yes, I think that's a good picture to think about it. I mean, here you have, I mean, this is just, here I plot only expectation values. But what this means is that if I have expectation values of oscillators, which are all different, it means that in reality, it's a coherent superposition. So if you go at the last time here, you have a superposition of these oscillators being all in different states.
Okay.
And then this vibrational state, of course, it's entangled because each molecule, for example, couples to the electronic degrees of freedom over the Holstein term. So each of these modes is at a different point in the superposition and couples to the electronic degree. So each of them entangles sort of with the electronic degrees of freedom. And that's how I like to think about it.
Okay. All right. Thank you. Thank you.
Sure.
You can continue, Professor.
Is there another question?
No, you can continue.
Okay.
Thank you very much.
Good. I'm very close to the end. Anyway, so right. So I was talking about these extreme configurations because we find that the nuclear distributions, they not only shift, but they also tilt. So we define this tail weight, and we define it in such a way that we take a weight that is like 1% of the total weight in the case where you don't have any cavity. Then we just sum over the weight of all of the molecules, because of course this is now going to be a very small effect because it's really just extreme configuration of one molecule, but we have many molecules. So if it has an effect, it should be a macroscopic effect. So we sum over all of the molecules. And I now also go back to, as I mentioned in the beginning, it's important to distinguish cavity excitation and molecule excitation. So I show results for both cavity excitation and molecule excitation. And on the left side, I compare vibrational entanglement. And on the right side, I compare this tail weight. And the cool thing is what you see, or what you should see, is that I show it here as a function of disorder. With disorder, this entanglement gets larger in both of the cases, cavity excitation and molecule excitation. And also this tail weight correspondingly becomes large exactly at the points where this entanglement is large. So it shows the same type of behavior, really. Another minor point I want to point out here, sort of the lines are really the mean value of the entanglement of this tail weight. And all these other small points you see here, they're all single disorder realizations. And it's important to point out that this is not a Gaussian distribution. So they are really partially very widely distributed, these points. So just to give an idea about the distribution, we show here each disorder realization. Okay, and the other cool thing is also here on the right side, I show again the these different tail weights that we get. And I also compare it, there's a little dotted line here. And the little dotted line is the one that if in our simulations, we would neglect any type of entanglement with the vibrations. In other words, if we would do this cavity-Born-Oppenheimer approximation. And then you see that this effect, in the sense that these tails of the distribution modify drastically, it really goes completely away if you don't allow for this vibrational entanglement. That's what this plot should show you. And finally, the last thing I wanted to show is now an important question, of course, how does this whole thing scale with the system size? And this is where it, as I promised now many times, it becomes really important if you first excite the cavity or if you first excite the molecules. Because here's on the left side again, the vibrational entropy, and here's this tail weight. And you see that if you have a cavity excitation, we find that this disorder enhanced entropy, it remains a robust effect as a function of n. Whereas for the molecule excitation, if you make n larger, this effect slowly goes to zero. And we can naively understand this just doing, for example, a perturbative estimation of how much weight is transferred away from the initial state. And we find that in the cavity excitation case, this goes as w squared over gc squared, so this is independent of n. Whereas for the molecule excitation, we find that this goes as wt, so it also changes with time. And then it goes as 1 over n, so it gets stamped away if you increase the n. Okay, but this is the end of my talk. So just to summarize the take-home messages. So what we really do is we take this physicist spherical cow approach with minimal models just to try to understand some fundamental effects in cavity-modified chemistry and transport. And don't get me wrong, even the super simplified models, they get extremely complicated if you want to numerically simulate them exactly. And so we use advanced numerical tools and quantum optics tools in order to solve the dynamics of these models. In the first part, I told you that if we neglect vibrational states, then we found this very interesting effect of these semi-localized dark eigenstates, which are states that kind of look like localized, like Anderson localized states, but they are localized not on one, but on multiple sizes. And that's why they have very strange properties, for example, in terms of the IPR or in terms of the level statistics. And they, of course, have direct implications for the transport properties of the system. And in the last part of the talk, I gave an example of how these semi-localized states are very important for modified vibrational dynamics, because they lead to a redistribution of the energy from one molecule to other molecules in the energetic vicinity. And that's really leads to very complicated disorder-induced vibrational dynamics, and therefore is disorder-induced vibrational entanglement. And in particular, really also to non-Gaussian shapes of these distributions. And another message is that one really has to go to beyond cavity-Born-Oppenheimer approximations if you have disorder in the systems. And yes, and we have this very cool matrix product state codes, which allows us to simulate dynamics of like 150 toy model molecules, and we intend to apply this algorithm for many more systems in the future. And with this, I'm at the end. So thank you for your attention.
Thank you very much, Professor, for an amazing talk. Definitely sparked a lot of questions. And there's still some questions. First, Madhu, and then Professor Hoyle again.
Hi. Thank you for the talk. Excuse me. So you mentioned various phenomena like transport and modified nuclear dynamics when you excite a state of the localized basis, like either an individual molecule or a cavity. I'm wondering what happens if you excite a dark eigenstate. Like, will you be able to, like, will the transport property change a lot, and then will you be able to get modified nuclear dynamics like in the second part that doesn't vanish with the system size?
Well, it means it depends what you mean by dark eigenstate. If you excite a full eigenstate of the system, obviously nothing's going to happen because it's an eigenstate. There's going to be no evolution at all. Now, of course, what you could do, you could sort of excite sort of a semi-localized states that would be an eigenstate if you would neglect the vibrational degrees of freedom. And but then I don't think anything much interesting would be happen, because then you would not get any type of interesting excitation transfer dynamics anymore, because from the electrophotonic part, it would be an eigenstate, and this part I think would not evolve much. And then it would be simply, I think, these two oscillators that you would excite initially at its two electronic degrees the corresponding oscillators, they would start to oscillate. And that's my guess. But if you would excite exactly, I think the interesting question is why, because if you would excite, because you can excite them also through the cavity. But you maybe, of course, if you excite really one eigenstate, then there would be no dynamics. But if you would maybe excite a bunch of superposition of these dark eigenstates, and then there could be some interesting dynamics only in a submanifold of these dark eigenstates, and then maybe there would be something more interesting going on.
I see. Okay, thank you.
And now, Professor Joel.
Oh, hi, Johannes. That was a really wonderful talk. Can you just go to the next slide, please? Sorry, even one more. Yeah, so here again, so when you say you excite the cavity, so I imagine that when you excite the cavity, then it rapidly oscillates into the bright mode, and then maybe a little bit of the dark states. So, but I guess what I'm a bit confused, like, wouldn't it be like you're basically claiming that there's a large difference in these, say, yield of the reaction if I do either of them? So if I excite the molecule or the cavity. So I think I understand that, but now I have a quick question. So even in the absence of disorder, the dark states are also semi-localized in some bases, right? Like in the Schur-Weil basis or something like that. Like, I don't understand why you need disorder to see all these effects.
No, I mean, you could, if I would really go to a toy model and I would really crank up, for example, this vibrational coupling term, I would also get a much larger mixing of the dark states with the bright mode. Or if I would add some disorder to this term, then it would be even stronger. But yes, but I mean, it's just really in reality, if you look at like vibrational energies, right? I mean, these numbers are not completely crazy. There is like something which is sort of semi-realistic. And the disorder, like the diagonal disorder, is really the term that does sort of the mixing here in our problem. But I fully agree. If you also get mixing from the other terms, it's just really that we believe for semi-realistic numbers, really it's the disorder that's the crucial.
But even if you don't have disorder in the, let me think about this question. So I guess even if you didn't have, maybe my question is not well formulated, but even if you didn't have nuclei, I mean, the dark states can also be semi-localized in some bases. Obviously the basis is arbitrary. So I guess I'm a bit confused why only in the presence of disorder this entanglement becomes large. Do you see my yeah?
Yeah. Okay. Again, I think this is connected to the question we had earlier, and I really actually believe it's this two effect. It's not only this excitation transfer, but it's really only just the fact that you have disorder, and because of this. This order, you get different excitations on different molecules. And because you have different excitation, different molecules, they all oscillate differently.
Okay.
So it's not so much the amount of excitation you transfer, it's really also the fact that they are like different excitations. And I think that's what really this entanglement.
But then the question I have is, okay, so I know why I was mentioning at the beginning this question about, so when you excite, say, the cavity rather than the molecules, then the cavity can exchange energy with the bright state. So how do you know in your plots that your differences in yields or in entanglement entropy are not due to the bright state dynamics rather than to the semi-localized states?
So I mean, to be clear, if you excite the cavity, it's the bright and the polarity states are very important in the system. I mean, I didn't have time. I showed more, really just most of the plots for the. Wait, let me just quickly go to this slide. I think I have a plot on this also here somewhere. Yes, this one here. Right. If you look at, so this is the similar plot you would get if you excite the cavity in the beginning. Mm-hmm. And there, what we see, what actually happens is that you really have, if you look at this plot again, this is the excitation transfer. And there you really, because you have this Gaussian disorder distribution, it's really, and you excite the cavity in the beginning, it means you put population in the polariton states in the beginning.
Yes.
Then we find that like the states which are close to those two polariton states, because I have, this is large disorder, this is GC over 2. So I have states which are close to the polaritons. And then the excitation goes from these polaritons to those two states, and then those two are the ones that start oscillating most.
I see.
Right, so it's a different mechanism. So the semi-localization I really only claim to use for the excitation hopping from molecule to molecule. For the cavity excitation, something else happened. It's just really, I didn't have time to really go into the details for this.
Okay, just one very last quick comment. So maybe this is a stupid question, but when you look at vibrational entanglement, the way you explained how you look at these metrics of entanglement, it seemed to me that you can look at either system. So if you just look at the entanglement, the electronic entanglement, why do you choose to look at the vibrational one rather than the electronic one?
Equally interesting, I fully agree, but we just really, a motivation was to analyze like when can we do this separation, when can we do this Born-Oppenheimer type approximation.
Okay, yes, sounds good.
But yeah, I mean, other entanglement, they are equally interesting.
My understanding, there are papers in the chemistry community, but one by Ignacio Franco and Arthur Ismailov, that say that Born-Oppenheimer doesn't necessarily mean lack of entanglement. I need to understand those claims well, but I think that seems to contradict to what you are saying, though.
Well, I mean, there's a lot of, you can add extensions to sort of Born-Oppenheimer. There are also different definitions. I mean, what I call sloppily, I call the Born-Oppenheimer. First of all, I would call it cavity Born-Oppenheimer. And then maybe not even that, because what I really mean by that is that I do the simulation and I enforce a product state between the vibrations and between the electrophotonic degrees of freedom. Let's call it product state ansatz.
Okay. Thank you very much. That was very interesting.
And now, on a final question from Dr. Ruth Tikauer. You can talk now.
Hi, thank you for the nice talk. I just have a question to. I want to clarify one point. Are you saying that, but through this dark states of semi-localization, the direct coupling between molecules is enhanced?
I'm saying no, it's not a direct coupling. It does not show in the Hamiltonian. But what I'm saying is because of the mixing of the diagonal disorder with sort of the mixing that the diagonal disorder does between the bright and the dark states, because of this, you have new eigenstates. And these eigenstates, they lead to an excitation transfer, which is very efficient between a few molecules. So what I'm saying is, in a certain way, this is also the story about this vibrational dynamics, is that if you don't have the disorder, then your excitation kind of starts to get diluted between all of the other molecules in the system, if it would be a fully symmetric system. But if you have disorder, then because of this semi-localized state, this excitation is very efficiently transferred to a few other molecules, not to all of them. But there's a larger excitation fraction now at fewer molecules. And that's what I'm saying. There's an efficient excitation transfer between fewer molecules because of this effect.
Okay, thank you.
Sure.
Okay, it seems like those are all questions. I do have a small, maybe naive question. So in terms of the semi-localized dark state that you showed, it seems to be in like the general picture that you have them roughly delocalized over only 2 molecules. Do you, if I understand, that's like without taking into account the nearest neighbor hopping between the sites, but is there any parameter of that hopping in which you don't only have semi-localized states, but also nearest neighbor localized states? And if that has any effect on any transport properties?
No, I mean, you can, I mean, with disorder, you cannot get, I mean, you only get it when you have a disorder realization where nearest neighbors are just by chance at a similar energy. Really, what the hopping term does, the hopping term, it really wants to delocalize. I mean, the hopping term really wants to make your states Bloch states, which are Bloch waves through your system.
Okay, so the semi-localized states are still like delocalized over roughly two
unless-
arbitrary sites. So there's no
Unless,
way
of
to
course,
like.
you would. Yeah, I mean, exactly. You cannot say it depends on your disorder realizations. I mean, if you can control somehow that you tune like two into close resonance, then those two would have semi-localized states which have weights close to each other. So that would be one
That makes
possibility.
sense. Okay, I guess that will be all then. Thank you very much. Sorry, we're a little bit over time, but that's because the talk was very exciting, I guess. We had a lot of questions. And yeah, so the next Polarized and Chemistry webinar will be announced. We'll be announcing it on our social media and through the email very soon as we have the information. So thank you everyone very much. And I hope you have a good rest of the week. Thank you again, Professor Johannes Schachenmayer.
Thank you very much. Bye-bye.